Okay, got that? Yeah. Okay. Yeah, a few things to be doing. So, work is being done in this picture. What things are needed for work to be done? Well, there has to be a force. In this case, it's with the shovel. And also, with work, usually you're making something move. So, what's moving in this picture? The dirt, the ground, yeah. There's a displacement, usually in the direction of the force, you know, so you're doing work if you apply a force to move something. And lastly, the force is usually over an area. So when you apply a force, it's usually over an area, you know. It's not like a little point, usually, not always though. Anyways, on to the formal definition in physics of what work is. So does anybody know the formal definition of work in physics? Harry, do you know? You look like you might know. Are you sure?
Yes.
Okay. Anyone else? The work done.
No, the unit.
What's the unit?
Joule.
Correct, yeah. The work done by a force acting on a body along the direction of displacement multiplied by displacement is the work. Simply, as a formula, work is force times distance. So work is the product of force and distance. So if you were to look at this formula, yeah, what would be the unit for work if you were looking at this formula? What would it be? Newton meters, yeah. The units are Newton meters. However, we have a special unit. You mentioned it, Zach. What's it called? Joule. But 1 joule is just 1 Newton meter. So we can say 1 joule of work is performed when 1 Newton displaces an object by 1 meter in the direction of the force. Okay. So that's our definition of work and joule. I'm tired. I am tired and I'm hungry.
No breakfast, sir?
No, I had breakfast. I'm just hungry. I'm going to split a large pizza with a teacher at lunch. I'm looking forward to that. They have some offer on Tuesday in the pizza place. The one near the
Across
school.
the road?
Yeah,
By
that
the intersection?
yeah. There's some Tuesday offer or something for a large pizza.
So,
Mm.
for our definitions, for all of physics, will we get like a standardized list or no? Because
The definitions, they're really flexible in the exam. You know, they're just looking for certain keywords to be mentioned.
Yeah.
So, like, for example, this definition here, you know, I could say something like, work is the product of force and displacement along the direction of force. So, the 2 key words I would need is some word that means multiply, like product. And also for the second mark, they want to see some mention of the direction. Yeah. Do you know? They're not looking for a word for word definition. That's too demanding of the student.
my governing body did that.
Word for word
Yeah,
definition?
word perfect definitions.
That's no good. That's too hard. That's too
So
hard.
we like this list.
A list, yeah.
Just with definitions for every kind of topic.
Yeah. I prefer if the students can kind of remember and then put in their own words.
I think that's better, more understanding than.
Yeah, it's easier too. Okay. Continue? Yep. Where and what is doing the work in each of the following? So the first one, a mother lifting her baby up from the ground. So who's doing the work? The mother. And the force? What direction? Yeah, it's an upward, it's a lift, isn't it? And the displacement?
From the ground.
Yeah, it's the distance the child moves, isn't it? A woman pushing a large box across the ground, the force? Yeah, well, like her hand, the pushing, yeah. And the distance, the x, the distance across the ground, yeah. Now, again, a little harder. A man kicking a football, so the force is provided by his foot. But what's the distance?
It'd be the distance the ball moves while he's in contact with it.
Yeah, it's the distance the ball moves while he's in contact with it, while his foot is touching it. It's not the distance the ball moves, just the distance it moves while his foot is touching it. Yeah. A child hitting the wall, so the force is obviously in his hand, but what's the distance? No, there's still a distance. It's just, it's hard to see and it's quite small. So the distance is the compression of the hand, you know, when he hits the wall. A father carrying his child. So similar to the last one, the force is the up force from his shoulders, and the distance is kind of the distance the child is, the compression in the shoulders. Yeah. Anyways, don't worry about this. I'm just getting us thinking about forces and distances. Yeah, and we'll have to talk about resolving. Let's skip that. So, just before we look at this example, if you have somebody pushing a block, and the distance here, the force is F, and the distance here is X, well, that's easy. The work that person has done is Fx. Fine. But what about if instead he is pushing at an angle? So that's F, and the angle here is theta. So the work now is not Fx. Yeah, very good. F which? Cos times X. No, because this is F cos theta, and this is F sine. It's the horizontal component, which is always the one, the cos is the one that touches theta. So what is the F sine theta doing? It's not doing any work. The F cos is doing the work. What's the F sine doing?
Reaction.
Yeah, the F sine, to be more precise, is reducing the reaction. This or should equal the weight. However, because of the F sine, you have F sine plus or equals the weight. So is the or bigger or smaller? Well, it's smaller because you have the F sine as well. So which component is doing the work? The horizontal. And the vertical component is just reducing the reaction force. Now you might think, well, that's kind of a waste. And it is a bit of a waste. It'd be better if he puts all the force horizontal. But there are some times where you want to reduce the reaction force. Does anyone know where you might want to reduce the reaction force? No, not this. Not this. So I'll tell you, we don't worry about it on this course, but later you'll discover that reducing the reaction force reduces the friction. but it's not something we worry so much about on this course. Anyways, this example here, a woman pushes 100 kilograms on a smooth surface by a horizontal force. The block starts at rest and reaches 1 meter per second in 5 seconds. Okay. What's the acceleration? Can we calculate that? We know how to do that, don't we? Yeah, so let's calculate that first. You can tell me the acceleration.
It's V minus U, right?
Yeah.
Negative 0.2.
Oh, it's definitely not negative.
0.
It's 0.2. 0.2. What's the distance travelled?
5. No,
Mm-hmm.
2 meters.
Are you actually calculating it or just guessing? You can calculate it. S equals ut plus a half at squared. So, what's that, like 2.5 or something?
2.5 times 0.2 times 1. 21.
Oh, come on, you're making your teacher sad, tired, and more hungry. What's the distance travelled?
Half AT, yeah.
2.5, which is what I said. Yes, 2.5, right? Right? So, the next part's what's the force? How do we get the force? What formula? F equals ma. No, stop, it's not 2.5 times anything. 100 times, 100 times what?
0.2.
Yeah, which is 20 newtons. How much work was done? Well, it'll be 20 newtons multiplied by 2.5, which is 50 joules. Right? And then lastly, if she pushes at 10 degrees, then it will be 25 cos 10 times, oh sorry, not 25, what was the force, did we say? 50 newtons?
Yeah.
The force was, no, the force, sorry, was 20 newtons.
Newtons.
So it's 20 cos 10 times 2.5.
49.4.
49.4 joules. Slightly less by pushing at this angle. Is that okay? You don't look okay. Are you okay, guys? What class did you have in 9?
Maths.
What topic were you doing?
It's
Oh.
called binomial theorem.
Okay. Hang in there. Right. Do you need to write anything down from this? Is everything okay? Yeah? Right. There's another element at play here. So, here's a picture of a ballerina. Tell me, why is it harder for her to stand on one toe than two? Like, her weight is the same. So, what's the difference?
Area.
The area is different. How has the area changed?
It's much smaller.
It's half. Well, it's actually less than half if she's standing on her toes. Yeah. So there is a huge, what's the word? Do we know? Not pressure, yeah. There's a huge pressure here. Like really, it's huge. Because, you know, everything is on, I don't know, 2 toes? I mean, not all her toes are, like when you think about your foot, not all her toes are in contact with the ground, right?
Yeah.
It's like, is it 2? 2 or 3 maybe, yeah. So, if you want, oh my goodness, if you want to see something horrible, go to Google Images and type in something like ballerina's toes damage or something like this. No, don't do it now. You'll be horrified. It's really a lot of force. It can cause a lot of damage. Okay. So, yeah, you're right. There's this thing called pressure. Do we know the formula for pressure? Force over area. This is, for some reason this is stuck now. Whoops. So, pressure means how much something is pushing on something else, like roughly. But mathematically, it's exactly what you said. It's force over area. Now, what if you look at this formula, what's the units for pressure? If you were to look at this formula.
Newton per
Newton per meter squared,
Pascal.
which is called the Pascal, yeah. The units are pascals, and we say, well, what do you think? Well, let's practice making a definition. We say 1 Pascal of pressure is,
1 Newton.
yeah, go on, yeah, 1 Newton of force applied over 1 meter squared. Yeah, something like this will be fine in the exam. There's just one tiny word that you might need to include. So it's when 1 Newton of force pushes at right angles, it needs to be perpendicular over 1 meter squared. Yeah. So wait, if you want, your definition is fine. Just add in the words right angles or perpendicular. So what did you say? You said 1 Pascal of pressure is when 1 Newton is applied over 1 meter squared at right angles. And then you're fine. Or you can just write mine down, whichever you prefer.
How many if you do this right angle?
90 degrees,
Oh.
perpendicular. Yeah. It's the opposite of wrong angles. Yeah. Wrong angles are, what are they? Minus 90 or left angles? Yeah.
What is called a right angle?
I think the only reason it's called a right angle is because when you draw the triangle, it's usually on the right, the 90 degrees. I think I don't know.
So is that because most people would draw a triangle with it on the right?
Yeah, I think so. Which then makes me wonder, then in Saudi Arabia, do they call it a left angle?
Yeah.
Because the
So
triangle's on the
people
left,
Or,
you know?
or people who are left-handed and right.
Yeah.
You know how the one
I don't know.
tends
I don't
to
know
favor
why it's
one
called.
side.
I don't know. I think right angle because it's on the right.
Yeah.
Perpendicular is a bit more precise. Okie dokie, we got that, yeah. So let me have a look at the next one now. Oh, it's the same, yeah. So it's the same as 1 Newton per meter squared, is what we said. Okay, we're back to the question I had earlier. Everything's the same, right? The only difference now is we have the area of her hands. My question is, what's the pressure? So, what did we say the force was earlier? 20
newtons.
20 newtons, okay. So there you go, you have the area. Give me the pressure.
How much is 0.01?
Oh, you know that, Zach.
It's 10 times.
Yeah, 0.01.
So it's 100 over 1.
Are you telling me or are you asking me?
Let me just go check. Centi, yeah, 0.01. 20 newtons. But the direction would be the opposite direction.
Pressure for this course, we don't care so much about the direction, although I know we really should because it could be a positive or a negative. Do we have an answer? What you get, Dorian?
20. What?
What? Say again?
2000?
2,000 pascals. 1,000 pascals. What did you get, Zach?
20 over 1.
20 pascals. Great. Wonderfully different.
Is that force over area?
Yeah, no, I know it is. Yeah. What did you get? Yeah. 20 pascals, the same as Zach. Okay. So, no, wait, Dorian, you know, you could be the only one right, or not. Harry, what answer did you get? 20. Uh-oh, it's not looking great, Dorian. What did you get? 2,000. Oh, okay. So we have, is that, you got 2,000? So we have 20 and we have 2,000.
I got 1,000.
Oh, 1,000. Great. We have 3 different answers. Let's see which is the right answer. Maybe you're all wrong. It's possible, right? So first, let's take care of the area. It's 100 centimetre squared. That's no good, right? We want it to be metre squared. So that's 100 centi squared, metre squared. That's 100 times 0.01 squared times metre squared.
Yes. I'm wrong.
So, you could be right, Dorian. What's that? 10 to the minus 4, isn't it? 1, 2, 3, 4. Is that 0.01
0.01.
meters squared?
Mm.
So the pressure is the force over the area. What's the force?
20.
20. And what's the area?
0.02.
0.02.
2 hands.
Mm.
Oh, damn.
That's 10 over 0.01, which is 1,000 newtons. Who said 1,000?
I did.
Did you, or did you say 2,000?
I said
I said
1,000.
2 something.
You said 2,000. Congrats.
Yeah.
Yes, you were the only one who got it. Well done. 1,000 newtons. I deliberately tried to trick you with the 2 hands.
How do we know it's 2 hands or one?
How do we know people have 2 hands?
No,
And
They mentioned
One
it in the
hand,
question.
2 hands.
Ah, okay.
They mentioned it.
Have a read again.
Oh, her hands are each.
Oh, each. Oh, jeez.
Yeah. Yeah, each 100. Instead of total 100.
Of those big hands.
100 centimetres square? I don't think so.
No, that
6
would be
by.
10
That's roughly 10 by 10, which is kind of reasonable,
Um,
isn't it?
Well, my hand is.
What's
Yeah.
her hands are quite big then.
No, they're
No,
not.
not really.
They're not.
what's your 2 lengths, Dorian?
Well, I can't. If you count it like this, that's not good.
Yeah, but yeah, we kind of let's
You have to do it like that.
At the one-
let's do the middle finger to here. What's that?
The middle finger,
Yeah, this one, the second tallest.
that's the fourth finger.
Whatever it's called. This one,
And
the second tallest finger.
roughly 15 centimeters.
And then across.
Roughly 8.5.
So 15 by 8 is about 100.
She's tiny hands.
Yeah. Yeah. She has Trump size hands. Yeah. Right? Okay. So this lesson, not too difficult. We can go on to the next lesson in a few minutes, which is, what is the next one now after work? Conservation of energy. That's a nice topic. Okay. So if you just want to try these ones for a few minutes, 5 minutes or so. I can close this.
Yeah. Is the next one with the elastic and inelastic?
No, not yet. No. That's you're thinking of
Conservation.
conservation of momentum, which is coming up in 2 more after this.
Energy is kinetic.
Kinetic and potential, yeah.